All right, got a lot of questions concerning the Organic 2 homework, so let's get started. First question is question 25 and 26. These are both Wittig reagents, so give me a minute to bring them up. Let's actually make sure that this is doing what it's supposed to. Yep, there it goes. So we have benzaldehyde. Reacting with the Wittig reagent. Now the Wittig is going to be this big phosphorus group hanging off. We put phosphorus with a whole bunch of stuff around it. The big thing here, and the reason why it's kind of not showing you that C6H53, that's triphenylphosphine, TPP. TPP, actually a very common reagent used a lot, both in organic and inorganic chemistry. The big thing here, though, is that it's this part here. So what we're going to do is we're going to clip our ketone or our aldehyde. We're going to clip our phosphorus carbon bond, and we're going to create a double bond between. We're going to replace this ketone or this aldehyde with a double bond to whatever is attached to the Wittig reagent. So basically, cut that oxygen off, cut that phosphorus off, and we form a double bond here. So check the solution. Yes, I don't feel like drawing it. Yep, so that's what you're going to end up getting is this compound here. This is a benzene ring, a cyclopentane ring connected by a double bond to one of the carbons on the site and the pentane. And I'm guessing that's kind of the same thing for question 26 here. Wittig reagents, they're kind of like alkene metathesis. It's a lot of information in the theory that can kind of distract you from the big outcome. So again, if we look at question 26, we've got cyclohexylmethylketone. Cyclohexylmethylketone. And our Wittig reagent, we've got phosphorus with that triphenylphosphine around it, TPP. Double bond it to, in this case, just a methylene. When we make the Wittig reagent, basically we're going to cut the phosphorus carbon bond. We're going to cut off this oxygen double bond, and where our oxygen double bond is, or was, we're going to put a carbon-carbon double bond to whatever this functionality is here. So we're just going to have CH2. And what we're going to end up here is, I'm sure there's some unique, there's some way to name this, but basically we're going to end up with this cyclohexane ring, carbon-carbon, and then we have a terminal alkene here. So this is the power of the Wittig. I keep calling it pseudo-Wittig. The reason I keep calling it pseudo-Wittig, I did alkane metathesis in grad school, and we used the pseudo-Wittig pathway. So that's why I keep saying it. The Wittig pathway uses the triphenylphosphine, the TPP, to replace ketones and aldehydes with carbon-carbon double bonds. And that's actually kind of the power of the Wittig reagent. It's very hard to do these types of reactions other ways. All right, so we got that one down. (25, 26, already did those, 29, 35, 36, 38, 40, 41, 42, and 43. So let's get to 29. So 29. Hydride reduction with LiH4 or NaBH4 with S3-methylfurbutyl has been reported in the chemical literature and gives two the structures of both alcohols and the ketone. So this is just kind of a mechanistic nuance with lithium aluminum hydride and sodium borohydride. So let's draw it first. 3-phenyl-2-butanone. And it's an S. Phenyl. Benzyl. So phenyl is going to be benzene ring connected directly to it. And then the S, let's see here, 1, 2, 3, it's counterclockwise, so this would be a wedge. So whenever we work with something like sodium borohydride or lithium borohydride, we get reduction of the ketone or aldehyde to an alcohol. The thing is that if we do end up generating a chiral center, we end up generating a racemic mixture of both. So we'll draw them both here. So we can have one where the lithium aluminum hydride attached from the front, the board, and what this will do is put the alcohol back, or we could have it attacked from behind, and this will put the alcohol forward. So we don't change the chirality here, we still have the S and the S here, but in terms, this should be changing. Yeah, it doesn't change. I guess there is a conceivable way that would also change chirality. But we have both, we keep the S on here, but we're going to get both, let's see here, 1, 2, 3. We're going to get both the S and the R forms of the structure. Now, I always get confused about phenyl and benzyl. Oh, you're lazy. They put a pH because they're lazy. But yes, you actually end up with both of these. And again, it's because if we look at the ketone itself is actually trigonal planar. So it's an sp2 carbon. And this lithium aluminum hydride can either add to this side or the back side of the bond. And in doing so, this is going to give us a racemic mixture of both the R and the S alcohols. And again, this kind of comes up more if we end up generating a chiral center. All right. Next one. 35. Draw the product reaction as cyclopentanone with diphenylamine, paratoluene sulfonic acid, and benzene. Okay. Seems like this is a little bit ahead of where we are in the material. So I'm going to get rid of question 35. This is actually from the amines chapter. I'm guessing they changed the problem on me, or at least the representative problem wasn't there. So for question 35, I'm just going to pitch it. This will show up more when we get to reactions of amines and carboxylic acid derivatives. This is actually a weird one where the amine acts like a nucleophile. It will attack the carbon, and ultimately we get alcohol elimination. There's a lot more to it, but my guess is that when I looked at this problem, it was a ketone problem. This dimethylamine was probably not the representative, was not the example that I was given. So again, we're going to pitch 35, 36. Every semester I get rid of more and more questions on this homework. Reaction of cyclopentanone with semicarbazide. Seriously? Also going to get rid of question 36. I would not have picked that question. So my guess is they have changed the question. 38. Okay, so this 38 is actually a fair question. So 38 is a deprotecting problem. So literature gives a single organic product and good yield, draw the principal product of reaction. So this is kind of getting used to, these are what are called hemiacetals. And hemiacetals are protecting groups for ketones. So let's say you want to run a reaction that your ketone is particularly sensitive to. So like you want to remove a carboxylic acid without losing your ketone or aldehyde. This is a good way to do it. So this is your hemiacetal here. And all this HCl is doing is providing a catalyst. And what we're going to do is we're going to break off this hemiacetal and produce ethylene glycol. And we're going to recover the aldehyde. Make sure you can see all that. Okay, so what's going on here? If you look at the structure, you probably think this is kind of a weird thing you're looking at. At least for me, these are always the big tip-offs. Is I see this double ether structure. So again, this is what's considered your hemiacetal or acetal. I think these are actually acetals. But anyway, this is the end product of protecting a ketone or an aldehyde. And so whenever you see this, this is really a ketone or aldehyde in disguise. So it's really a protected aldehyde or ketone. So if you see this, you should immediately think it's probably this when I reacidify and we go the opposite way. We add the ethylene glycol with the base, and this gives us the acetyl. The nice thing is with these type of acetyl groups, they're protecting under basic conditions, not acidic conditions. Under acidic conditions, they decompose. But typically the reason we want to protect an aldehyde or a ketone is because we're running something like strong reduction or organometallic reaction. Those tend to only work under basic conditions. Acids decompose. So if you add acid to something like lithium aluminum hydride or sodium borohydride, they actually decompose. So this is kind of a nice consequence of the protecting groups is they're typically stable under conditions where we'd be running the reactions that would actually remove our aldehyde or ketone that we're trying to protect. And when we want to go back to, when we get done with the reaction, we start acidifying, and that usually decomposes whatever we were worried was going to interact with the aldehyde or ketone. 38. 40. So what key intermediate compound A must be prepared from cyclopentylphenylketone in order to synthesize compound B in 2 steps? So we have a carbon-carbon bond formation reaction followed by a functional group transformation. So reaction. Actually not too bad. This looks like a Grignard. So we're starting with this compound here. We want to go to an intermediate, and then we want to form this compound here. So 2 things we're doing is we're getting rid of the ketone, or 3 things we're doing. Getting rid of the ketone, adding a methyl group, and forming a double bond. So an easy way to do this is to go through an alcohol. And what we can do with the alcohol is we can remove this with concentrated sulfuric acid to give us the dehydration. So how do we do this? Well, it's just an it's just a Grignard. Or we can do an lithium or organolithium. So we have a lot of option here in terms of how we want to attack. We could do an organic cuprate, but ultimately it's some type of organometallic reagent where we add the methyl group. So we add, and then we follow it up with an acid workup, H2O plus, and then we do a further dehydration. So let me draw the structure to make sure I'm right. And mercifully, it's not going to make you like include stereochemistry. At least I'm guessing it's not going to, because that would be a nightmare. So I'm going to claim that we're going to go through this alcohol intermediate first. That would be correct. So the next thing I'm going to ask you what reagents are necessary to carry these out. Reaction 1, this is just, yeah, let's be confusing, use Grignards with chlorides. You're going to do the Grignard, the CH3 MgCl in this case, followed by an acid workup, and then 2 is just the sulfuric acid. And that's it. So yeah, the trick here was just kind of catching that we're going to have a dehydration reaction, which means we need an alcohol, and we can form an alcohol through a Grignard attack on a ketone. (41). By the way, I find it quite fascinating we talk so much about Grignard reagents and they're not used. A compound that's methylforming C4H8O contains a carbonyl group. Identify the group on the basis of the 1H NMR spectrum. C4H8O. And we've got a few approaches we can take to kind of narrow down what this is. Again, I'm not a huge fan of going straight from the NMR, but it is what it is. So we've got a really de-shielded carbon down at 910 ppm, and then we've got 3 carbons at 2. So that, carbonyl group, C4H8. Identify the compound on the basis of 1H NMR shown below. So we definitely have a carbon-oxygen double bond somewhere. We have, looks like a triplet. This is why I give you the tables. I did cheat and look at the answer. Okay, so this is actually an aldehyde. 1, 2, 3, 4. So how did we get there? We've got 3 here, 2 here, 2 here. This would end up being your triplet. This is a fairly de-shielded triplet. Oh, this is an awful, awful image. Actually, it's not a triplet. It's a doublet of triplets. So this is your peak at 2.4 ppm. This is your really de-shielded singlet down there at 9.9 ppm. Down here, we would end up getting a doublet. So your doublet, no, triplet, sorry. You would end up getting a triplet here. The triplet you're seeing here is that shift from 1 to 0.8. And then 2, this ends up being a quartet of triplets. So that really weird one at 1.8 to 1.6. That ends up being your structure. So kind of fair. I cheated and looked at the key, full disclosure. But yes, the hint here is that it's an aldehyde. And, oh, so this one down here wouldn't be a singlet. It would also end up being a triplet, a pure triplet. And so that's why you get that really strong shift down at 9.9. So I guess the tip off here would be like that you are seeing that super de-shielded hydrogen. That would be the tip off that you have the aldehyde. It is kind of giving you that outside information that you know you have a carbonyl. You know that you have 4 carbons that contain hydrogen. There's only 4 carbons in the molecule. So one of this has to be an aldehyde because that's the only way you can get a hydrogen on every single carbon. So it is a really good question, actually. Compound has the structure C7H14O. It has 3 singlets in the ratio of 9 to 3 to 2 at 1, 2.1, and 2.3 respectively. So we're going to cheat. We kind of know that we have to be working with an aldehyde or ketone, and since we don't have a really strongly de-shielded carbon here, this is going to imply that we have some sort of, we don't have an aldehyde, we have a ketone. So for ketones, so we have 3 singlets in a ratio of 9 to 3 to 1. So that 9 there are going to be 3 methyls. The 3 there is a single methyl. And the 2 there is a CH2 group. So we got a trimethyl group, we got a tert-butyl group. Finish out to an R. we have some isolated methyl group with nothing on it, and then we have a methyl group here that has, we have a methylene group of CH2, and then we're also going to have a carbonyl carbon. So let's count the carbons. We have 3, 4, 5. We have 3, 4. In terms of ones that contain, ones that we know about. So we have 3 for the methyl. Now, in order to kind of, so this would be a tert-butyl. We are also going to need to count the 4th carbon there. So I've got 1, 4, 5, 6, 7. And there's 7 carbons in this compound. So, backtrack. In order to get this chemical this singlet with a 9 integrated area, I need a tert-butyl group. That tert-butyl group contains 4 carbons. And so that's how I'm going to get my 9 singlets. For my area of 3, I need an isolated methyl group, so this R needs to be connected to other things. That's going to give me 1 carbon plus, and then, so I'm going to have a CH3 hanging off some R that has no hydrogens. And then to get my singlet with an area of 2, I need an isolated CH2 group that has something on both sides. So, and then I also need I need a carbonyl carbon. So this gives me 1, 2, 3, 6, 1 for that carbon that connects the tert-butyls. This gives me my 7 carbons. So how am I going to put this together in order to get this type of structure? So let's consider a few possibilities. So let's say the tert-butyl group is hanging off of this carbonyl carbon. Now I need to add a CH2 group and a methyl group, and I can't do that because these would be isolated, so this can't work. So now let me try. So again, this won't work because these would actually end up splitting each other, so I couldn't get the singlets. Let's try putting the CH3 group to the left of the carbonyl, and now we've got our CH2 group down here, and we've got our tert-butyl group here. 1, 2, 3, 4, 5, 6, 7 carbons. 3, 2, plus 9. That'll give me 14 carbons. So this is my guess here, is that I actually have a, it would be, so I had a student ask me, like, ketones are really annoying because they're named opposite from the way ethers are named. And she's right. So ethers, it's the length of the branch. Ketones, it's the alphabetical order of the branch. But I just wrote back to say it's actually, if you just memorize the functional class name, that always works. So we got 1, 2, 3, 4, 5. Pentanone. So this would be 2, 4, 4, dimethyl, 2 pentanone. Yep, and this is correct. So again, the way I work through it, if I have an area of 9, this is usually a tert-butyl group. If I have an area of 3, that's an isolated methyl group. And then to get my area of 2 and isolate it, I need a CH2 group that bridges but has things on it that have no hydrogens. And I know that my compound contains a ketone because of the IR bending mode. Plus, I'm kind of cheating. I know I'm in the unit aldehydes and ketones. So I need an additional carbon oxygen double bond somewhere in there. So then I just kind of messed around. I put the tert-butyl group on one side, then I attached the methyl group because I know that would give me isolated carbons or isolated hydrogens. And then I stuck the CH2 group to whatever remained. All right, 43. C7H4 and carbon 13 below, draw the structure. I don't like that question. I'm going to get rid of this one too. They did not label their solvent peaks. Good for them. Okay, so this is solvable. I just don't think it's a fair question. So I'm going to get rid of question 43. So that's all the questions I got emailed in advance. Other big things, don't forget if you're an organic, you have your exam the week after spring break. You need to go ahead and schedule it. Also, for those of you in Chemistry 152, you need to submit your oral report topics this week because they're due Friday. If you don't submit your topics, you can't give your oral presentation, and that's like 10 points off your exam, your grade in the lab. Definitely not worth it. So I'm going to switch the camera off now. If you got questions, I got the chat up. And yeah. Question got asked, a small question for data observation calculations. I know I asked this yesterday for clarification. The mass or volume we needed to calculate results. For the trial info is data and observations, everything else. Anything you use, so the thing is that you can report anything you measure directly. But as far as where that number comes from, you have to show it in the calculations. Now, the other thing to keep in mind is that the mass you calculated and the mass you measured were two different numbers. So you can't put the mass you calculated that you needed in the observation section because you calculated that, but you can report the mass that you measured. On top of that, there really is no reason to report the volumes you used in the observation and data section because that's part of your method section. Your method section tells me how you made the solution. So if you're reporting the volumes you used in your data and observation section, that doesn't really make sense because that wasn't part of your data and observations. You were making solutions. That was part of your methods section, and that would come up in your methods section. Slide 7, electron dosing. Do you have to pay attention to the R groups to see whether or not the diol forms when H2O adds from the diol? So, short answer is yes, it always forms the diol. Long answer is that it's an equilibrium. So when we have any type of carbonyl carbon, and we won't make statements here on what R and R prime are, they will always interact with water to generate this structure. The question is, which way does the equilibrium lie? So the more electron withdrawing groups we have for R and R prime, excuse me, the more this equilibrium lies to the right. The more carbon-hydrogen bonds we have, the more it's going to lie to the left. So short answer again is like, yes, it always forms. The question is to what extent, and we don't worry about that at this level. So we talk about protecting groups. Protecting groups are kind of an extension of this. So you're working with a diol, and the diol has that OH kind of like water. We're kind of oversimplifying here in saying that it's easy to form protecting groups. In reality, there are some groups that are super hard to protect, or the equilibrium doesn't lie very far to the right, so forming the acetyl is actually quite difficult. That is more of a graduate level course to start talking about ways you would force the reaction to form the protecting groups. But as far as like, does it form? Technically the answer is yes. Does it form in appreciable amounts? That's a different question. So an example of this from Chem 2. Chem 2, we talked about the solubility of compounds in water, and in Chem 1 you probably learned the solubility and insolubility rules, and you were told that certain compounds are insoluble in water. Example, this is calcium phosphate. And then in Chem 2 you learned that, well, actually it does dissociate. It just doesn't do it very much. So again, the case is going to be here. All aldehydes and ketones interact with water to form diols. They will all react with diols to form acetyls. The question is to what extent it does. We don't worry about that at this level. It's much more of a graduate level course, much of an organic synthetic chemistry kind of course. So big picture here, like it does happen. The extent to which is a matter of debate. You can make it happen more by adding electron withdrawing groups, but we're just going to assume it happens unless we have reason to think otherwise. Yes. So if water is given as a reagent, so you just have some aldehyde or ketone given water, you would have that formation of the diol. If your concern here is like practical, real-world situations, so a big thing in organic chemistry is drying your solvents, because if you don't dry your solvents, they contain water. Does this end up creating the diols? Yes. But unless that's like the only reagent you're given, the other thing to keep in mind is that if you have something like an alkene or an alkyne, those are going to react with the water more strongly. So I don't think you're going to be really given any problems where like you're given two functional groups and shows, or if you are, you're going to be given like pretty unambiguous like examples. But generally speaking, if you just see like an aldehyde or a ketone and you add the water, it's going to break into the diol. If there's any other functional groups, it's probably going to attack the other functional group first if that one reacts to the water. So yes, I'm going to say that qualitatively. I'm also going to put the caveat on here that I will answer a few questions, but if you want me to review your lab report, you're going to need to email it to me, and I will only review it once. So again, Max, if you want me to review a specific part of your lab report, you need to email it to me. But I'm not going to go through your lab report line by line, especially in a live stream, because that's what your one review is for. If you have broad questions, I will answer those, like, so where does this go? How do I format this? But as far as, again, I'm not going to read your methods section here in an office hour. That's what the first review is for. So let me download slide 66. I just cleaned off my desktop. You did, and if you want to include those calculations, they need to be in the results section, not in the data section. The method section, you explicitly can state what you did. So in terms of epoxide opening, where are you? Open epoxy range from the auction on the more substitute carbon for asymmetric epoxides. Okay, so if you looked at the book for the mechanism, yes, the mass that you actually measured, that's the data section. In terms of, so if you ever look at the textbook for how lithium aluminum hydride works, it's a big nasty mechanism. It's also an incorrect mechanism because aluminum follows, well, like the orbital theory, it doesn't follow Lewis theory. So we're going to look at it from a big picture standpoint. Lithium aluminum hydride is a big molecule, and the lithium here is just a counterion. What we really have here is an H negative and 3 H positives. Actually, no. Three H negatives. So generally what's going to happen here is the hydrogen is going to attack the carbon. And the reason why the oxygen goes onto the more substituted carbon here is that the less substituted carbon is the one that's actually accessible to the lithium aluminum hydride. This is just a big honky molecule. So we're going to get this structure plus the ALH3. This ends up being a neutral molecule with the lithium plus here. So that's the first step, is that we open up the ring, and it's just because the hydride, the H negative, ends up attacking the least substituted carbon just because it's more available than the most substituted carbon. Next step, with all these LiLH3, LiLH, lithium aluminum hydride and sodium boride reactions, we always follow this up with an acid workup. This is just a protonate. And that's how we get the alcohol. But that's kind of the big picture mechanism. Again, your book has a very, I would argue, overly detailed explanation as to how lithium aluminum hydride works. The better way, in my opinion, to think about it is that you have hydride attack. It's a nucleophile, and it's going to attack more, so less substituted carbon because it's more available, and it's going to give you the alkoxide, and then we follow it up with an acid workup. Again, I think your book goes in way too much detail about the mechanism of lithium aluminum hydride. I get what they're trying to get at with it. Um, but if we take a big picture look at it and we say, hey, it's Lewis theory and it's an approximation, I think viewing it like that makes a lot more sense and ends up giving you the right answer in the end anyway. Now, is what I'm showing you a very like oversimplified version of mechanisms? Heavens, yes. But the ester example as well. So the ester is going to proceed in 2 steps. And I'll draw the thing out. So again, if we, instead of looking at the big lithium aluminum hydride molecule, let's just treat it as a hydride source. First step is the hydride is going to attack the most positive carbon. We're going to attack here, and this is going to break off the alcohol to give you the alkoxide. Alkoxides are definitely more stable than hydrides. And you finish up with the aldehyde. The second hydride, the H negative here, is going to attack the carbonyl again. This will end up giving us a second alkoxide. And then when we do our acid workup, we protonate our alcohol and we protonate the other alcohol. So again, when I think about aluminum hydride, I don't think about the big lithium and aluminum source. I think about the aluminum as a hydride source, an H negative source. Organic chemists are free to yell at this video and tell me how I'm wrong. But for me, if you view the hydride as just a very, very, very good nucleophile, we're right back into nucleophilic substitution will actually be what we start picking up on the next test. And the hydride here attacks the most positive carbon. We get a CH bond, form the alkoxide because that's the more stable anion. Hydrides, the H negatives and the alkoxides don't react because they're both negative. This will end up being balanced by one of the lithium ions. This, as you start removing hydrides, you'll start picking up the positive aluminum. And the hydride does the exact same thing to the aldehyde. It attacks it, forms the alkoxide, and the goal here is just to basically end up with alkoxides because the hydrogens won't attack those. Final concentration and volume that is, I don't know what the is refers to. The final concentration is the results. And then starting concentration is the method section because that's the starting concentration of what you use. That's not really a data or observation. And the mass used is also data. Alright, hemicetals are half bonded, and then cetals are full rings. Gotcha. So the nitrile and the azides. Okay, so azides are an interesting beast. We haven't gotten to azides yet, so this is just more kind of a summary. So the nitrile, again, if we take the same approach of treating the hydrogen as a hydride source, the carbon's the most electronegative here. We're going to end up getting one attack. And then a second hydride attack to give us, this is a really oversimplified mechanism here, and -2, and then when we add our acid workup, H3O+, we'll end up forming the terminal amine. Now, this is a very bad looking -2. Oops. This is a very bad looking -2, but again, prove me wrong, right? So what will end up happening is that the hydride will attack the carbon because it's bound to the nitrogen. It's more electropositive, or it's more positive, and so we get double hydride attack. And then when we acidify, the nitrogen picks up the hydrogens. Azides are a bit more of a different beast. So the azide ion is kind of a weird one. So with azide, this nitrogen is 100% positive. We'll talk about this when we get to the amines chapter. Again, we're going to treat, I prefer to think of it as treating it with a hydride. And so we get our first attack. Second attack. And again, this is a really oversimplified version of what's going on here. I know that these charges make absolutely zero sense. But basically, because this nitrogen is positive, it's just going to keep getting attacked by hydrogens until you eventually saturate it. And you end up getting your NH2. And after your acid workup, you're going to end up getting ammonia. So again, it's all kind of the same idea. We're going to treat I treat the lithium aluminum hydride as a hydride source, an H negative source. It attacks the most positive thing. In this case, it's the nitrogen. And it's going to keep adding hydrogens to the nitrogen until it finally clips that nitrogen-nitrogen bond. And we end up forming ammonia and the amine. Now, for these, it's just converting to NH2. So for the nitrile, it's adding hydrogens to the carbon, and then that creates a basic nitrogen that will pick up hydrogens to give us the NH2. So the end result is the same, yes. So that's what you're asking. Is like the end result is that we're going to form NH2s. And forming amines is not the most trivial thing. We'll talk about that when we get to the next unit. But making those nitrogen carbon bonds, it's a lot easier for nitrogen to pop off as an H2 or an H3 than it is to actually do a lot of it. It's hard to control the amine chemistry, in my opinion. So this is just kind of a little toolkit for like making them from like nitrogen containing groups that are very easy to attach to carbon rings. So I guess I should say that more. It is hard to add an NH2 group to a ring. There's a very limited set of reactions where that will All right, we're back online. So for carboxylic acids, it's actually, so yeah, kind of a similar idea is that we're taking our hydride attacks. It's going to pop off that OH group, and it's going to give us an aldehyde to begin with, and the hydroxide. Our second hydride is going to attack. This will give us the alkoxide. And then we follow it with an acid workup to give us the alcohol. So yeah, again, the way I think of it is I just think it's a hydride source. Hydrides I've worked with a lot. So for me, the hydride, again, here it's going to attack the carbonyl, pop off the hydroxide. Now you got an aldehyde, and it does what it does to aldehydes, where it adds H negative attack, gives you the alkoxide. And the goal here is to get down to things that look like hydroxide, because those are way more stable than the hydrides. The H negative, if there is a hydrogen source, it will attack it to give you H2 gas. So when you did the reduction of benzophenone, and you threw the sodium borohydride in there, I think it's weird. Your lab manual is like overly proud of that 4-to-1 ratio that it's talking about. You actually throw a ton of sodium borohydride into that mixture because it's going to react with, it's going to basically react out the water and the methanol first before it starts reacting with your compound. But yeah, sorry for the cutoff there. It's kind of in the live stream though. So again, if you ever have questions, please feel free to email them in advance. These are not lessons. These are not lectures. These are office hours with lab reports. I will answer general questions. If you want your lab report looked over, you need to email it and you get one review. All right. Thanks for showing up, and I will see several of y'all tomorrow morning.